Hey everybody, it's Ripley back again. We're going to talk about integration using partial fraction decomposition. If you recall, partial fraction decomposition came from your pre-calculus experience. The reason that we're going to use it in integration is when we go to integrate what are called rational functions. If you recall, rational functions are functions of the form p of x over d of x, or p of x over r of x dx, where p and r are polynomials. So a rational function, for example, is something like, I don't know, 6x plus 7. This, by the way, is very contrived because I'm going to do something here in just a sec, to x squared minus x minus 6. All right, so this guy would be the p of x, this guy would be the q of x, and this whole thing together makes an f of x, right? So this is referred to, as a rational function. Now, this is actually the last of the techniques of integration, but it's a pretty, it's a pretty important one, all right? Because let's say, for example, that I'm going to take the integral of this guy, I got x squared minus x minus 6 dx, right? And I look at this and I'm like, let's go through our checklist. Haven't memorized it, crap. What else haven't I done? I can't do a u substitution, crud. What am I gonna do for integration by parts? Good Lord, not a trig sub because it's not of any of the forms and there isn't any trigonometry in it. Well, it looks like I'm kind of stuck. However, if you recall, now let's actually go through the process of doing a partial fraction decomposition. And if you recall, what that means is we are going to take this guy right here. We're going to turn it into 6x plus 7. I'm going to blow through this kind of quickly because you saw it in pre-calc, but I'll also take time as well. This is over x minus 3. And x plus 2. Now, when we are done, what we're doing is we're pulling apart this fraction so that when we're done, it's going to look like a over x minus 3 plus b over x plus 2. And the reason we're doing that is, think about that. If I can rewrite this integral as some constant a over x minus 3 plus some constant b over x plus 2 dx, look at how easy this becomes. This simply becomes a times the natural log of the absolute value of x minus 3 plus b times the natural log of the absolute value of x plus 2, right? Whoops, end absolute value, not a parenthesis. So let's go through the process, if you recall. Now, I bust this thing up because I'm allowed to do that, because I know that the sum of fractions creates a common denominator, and the numerator is the combination, a linear combination in this case, of those numerators over here. So remember how this works? What I do is I multiply through by the common denominator, which is x minus 3 times x plus 2. Now, some of what I'm going to do, if you recall, because I griped about this in pre-calc, is going to seem a little illegal mathematically speaking, but just bear with me for a sec. I get a times x plus 2 plus b times x minus 3, okay? Now, I am going to let x equal negative 2. And you may say, wait a second, Ripley, you can't let x equal negative 2. Negative 2 is not in the domain of the function. It's not allowed over here. Why are you allowed to do it? Well, I'm allowed to do it because I've gotten rid of those denominators. I get to ignore this function, which clearly does not include negative 2 in the domain. But this linear function up here, this linear equation allows for the possibility of x equaling negative 2. So let's see what happens when I do that. I end up with, let's see on the left, if x equals negative 2, I end up with what? Negative 12 plus 7, affectionately known as negative 5, is equal to a times 0 plus b times negative 5. Hey, that's pretty cool. So negative 5b is equal to negative 5, and b equals 1. Sweet! Well, that's cool. So now I've got b equaling 1. So let's change colors just so we can see that we're sort of changing modes. Now I'm going to let x equal 3. Do you see what I'm doing? I'm substituting in for values of x that make one of the terms disappear. Now that doesn't always work. We'll do a more complicated problem here in just a little bit, but I want to make sure that you, that you see what we're doing here. Whoops. All right, so where are we? If I let x equals 3, last time I checked, 6 3s is 18 plus 7 is 25. So I get 25 is equal to 5 times a plus 0. Well, that's easy. 5a equals 25. Looks like a equals 5. Now, let's go through this process. We'll just bring it over this way. I know that a is 5, so I can rewrite this integral as 5 over x minus 3 plus 1 over x plus 2. Now, I can check this really quickly in my head. Don't forget your dx. 5, if I cross multiply, I get 5x plus 10 plus x minus 3 is 5x, I'll do it right here, 5x plus 10 plus x minus 3 turns into 6x plus 7. Hey, that's what we started with up here. Yay, smiley face. Easy. And check it out. Watch how easy the integral is now. It's a piece of cake. I get 5. It's the natural log of the absolute value of x minus 3 plus the natural log of the absolute value of x plus 2 plus c. Now, you do have to be careful. There's a little cautionary tale that you have to be super careful with here. And that little cautionary tale, excuse me, is that remember your laws of logarithms. I could rewrite this if I wanted to as the natural log of the absolute value of x minus 3 to the 5th plus the natural log of the absolute value of x plus 2 plus c, and then if you recall, the sum of logarithms is actually the log of the product. So I can write this as the natural log of the absolute value of x minus 3 to the 5th times x plus 2 plus c. Now, why is this important? Excuse me. Well, it's really important because if you're taking a multiple choice exam and you get to this answer, like on the AP or something like that, if I get to that answer and then all of a sudden it's like, oh my God, I can't find it, whatever will I do? Well, you realize that you do a little bit of algebra and you use those techniques, okay? All right, now, the rule, I gotta make sure that everybody understands, because there are some rules in here that we really have to observe. The main rule of integration by partial fraction decomposition is if I'm going to use it, then the degree of p, so if I've got this guy, the degree of p has got to be less than the degree of q. Whoops, degree of q. Else, I long divide. I long divide. Now, you guys are going to hate long division, but that's okay. We'll do a quick little problem. This is actually one that I stole right out of a textbook because it's a pretty darn good problem. So bear with me. I am going to take the integral of x to the 4th minus 2x squared plus 4x plus 1 all over x cubed minus x squared minus x plus 1 dx. Now, you know that it's in the partial fraction decomposition section, which is fine. So we know that we're going to use that technique. Well, maybe you don't. I mean, let's go through our check marks or our punch list. First thing, have I memorized it? Dear God, no. What else do I need to look at? How about, can I do parts? Maybe. I reckon you could, but I don't recommend it. Let's see, no trig anywhere. So we start to lose techniques pretty quickly. Really, I've identified it as a rational function. So my first go-to, if I can't do a really quick substitution, is to think, okay, can I do partial fraction decomposition? Well, yeah, but not yet, because this degree is bigger than this degree. So what I do is I long divide. Now let me give you a quick little refresher on long division. I go x cubed, it's x squared, minus x plus 1, and I divide that into, now we're going to do long division, which behaves very much like regular old long division, but you got to be really careful here. Notice there's no x cubed term. So when I divide, I'm going to get x to the 4th, but I have to account for the fact that there's no x cubed. So I leave it as 0, x cubed, minus 2x squared, plus 4x, whoop, plus 1. Think of that 0 as being like the 0 in, if I do 107. Right? This is 0 times the tens value, right? 7 times the 1 value, 1 times the hundredths value. So that 0 is a placeholder for the x cubed term. Now I just follow the end of my nose and watch what happens. X cubed goes into x to the 4th, x times. I get x to the 4th minus x cubed minus x squared plus x. Now here's the way that I do this, because it drives me crazy because I'm really bad with negatives. Some of you know this. So the way in which I deal with that is put the whole thing in parentheses, slap a negative on there. I then change excuse me, I then change the negative into a positive and change everything's sign. So now I'm just adding everything. So those guys cancel. This becomes, whoop, just like long division, x cubed. This is minus x squared and then plus 3x. And then if you recall from long division, I bring this down to there. Now, how many times does x cubed go into x cubed? Well, 1 time. Let's go back to blue because that's going to be obnoxious. So plus 1, and I end up with x cubed minus x squared minus x plus 1, right? So and then I subtract and we see what happens. So here we go. Let's see. If I subtract these out, turn that into a positive, change sign, and then make that a negative. Those cancel, those cancel, those cancel, and I end up with what? 4x. So this guy can be written as x plus 1 plus 4x over x cubed minus x squared minus x plus 1. Holy smokes, this is hard. Math is hard. All right, so this integral then becomes x plus 1 plus 4x over. And I'm going to do x cubed. Now, I'm going to do something here because I can feel the eyes on the video going, Ripley, how am I ever going to be able to factor that? Well, it's actually not that hard. Watch, I'll show you. I'm going to factor it out right now because it's going to make our lives easier. I am going to factor out an x squared. I'm going to do it by grouping. All right, anytime that I see a quadrinomial or a 4-term polynomial, and I have to factor it, I start thinking in terms of groups. So I see x squared or x cubed minus x squared. So I'm going to pull out an x squared there, and it's going to leave me with an x minus 1, right? Now, over here, let's say I've got an x minus 1, and I've got a negative x plus 1. Hey, wait a sec. I can pull out a negative 1, and won't that leave me with x minus 1? So pull out a little negative 1 right there. Hey, now, don't forget your dx. It's like your vitamins every morning. Don't forget to take it. All right, now, as of right now, watch what's going to happen. I already know that this is going to become x squared plus x plus the integral of 4x over x squared times x. Whoops, what am I doing? X squared minus 1. Sorry. This is going to be x squared minus 1 times x minus 1, dx, of course. Good use of parentheses. Right? Now, you see where the x squared and the x came from? Well, the antiderivative, whoops, that should be x squared halves, shouldn't it? The antiderivative of x is x squared halves. The antiderivative of 1 is x. You guys were going to call me out on that. I caught it. I rule. Okay, now, hopefully you can see, because remember, if you recall from pre-calculus, let's do an implies arrow here. So I can ignore this for a little bit. All right? I'm going to use an implies arrow. If you recall from partial fraction decomposition in pre-calculus, it was really important when factors were repeated. Now, I know that x squared minus 1 factors into x plus 1 times x minus 1. So I can rewrite this part of the integral as 4x over, well, I got an x minus 1 here and an x minus 1 here. So this is x minus 1 squared, and then times x plus 1. This is dx. Now, let's dig way back into the Wayback Machine. If you recall, the rules for partial fraction decomposition, I'm going to change colors to black, was, like in this case, I've got 4x over x minus 1 squared, and then I've got x plus 1. Now, over here, let's do this sort of parenthetically right here. Do you remember if I had something like this? If I had 3x plus 1 over x squared plus 1 doesn't factor times x plus 3, right? Remember how this worked? Because this is quadratic, this guy right here is quadratic, I would write that as ax plus b over x squared plus 1. In other words, the numerator is always 1 degree less than the denominator. Well, if the denominator is linear, then the numerator is going to be a constant term, right? So this would be c over x plus 3. However, there is an exception, and the exception comes when I've got a repeated factor. So if you think about it, I've got x minus 1 squared, which is, technically I can multiply it out and I get a polynomial, which you could do, it just makes the algebra harder. If instead I simply go a over x minus 1 plus b over x minus 1 squared plus c over x plus 1. Now, if you don't recall this, go back to my pre-calculus video and watch the video on that because it describes why this works and why it makes our lives easier. For the time being, let's just go through this problem, okay? So the common denominator is x minus 1 squared times x plus 1. We multiply the whole thing through by that. So I get 4x is equal to, now, what is this denominator missing? It's missing an x minus 1, and it's missing an x plus 1. So I'm going to go a times x minus 1 times x plus 1, right? That's what it was missing. In other words, once I've cleaned it up, this is what happens. What's missing from this denominator? Well, an x plus 1. So I'm going to go b times x plus 1. And then last but not least, I've got plus c, and it's missing an x minus 1 squared. So I've got x minus 1 squared. And then we just go through the same process. Let's change colors again. Let's let x equal 1. Well, if x equals 1, then I get 4 equals, okay, this term goes to 0, this term goes to 0, and I end up with a 2b because last I checked, 1 plus 1 is 2, 2 times b is 2b. Hey, look at that. b is equal to 2. Fabulous. How about let's let x equal negative 1. Okay, so what happens there? I get negative 4 is equal to, okay, this term goes away, this term goes away, negative 1 minus 1, excuse me, negative 1 minus 1 is negative 2 squared is 4, positive 4. So I got 4c. So c equals negative 1. So we've got b and c. The problem is, what should I let x be? Because we burn through all of our values that make nice, tidy little zeros, right? Well, it doesn't really matter because I already know what b is and I already know what c is. So I'm just going to let x equal 0. I can let x be anything, right? Because really, I could let it be 17,000, but it's going to make the work a lot harder. So I let x equal 0 because I like 0 because it makes pretty terms. In this case, it's going to be 0 is equal to, now let's look close. For a, I'm going to end up with a negative 1 times a positive 1. So I get negative a plus, now remember, b is 2. So when I let x equal 0, I get 0 plus 1, which is 1, times 2. So this is plus 2. If I let x equal 0 here, I get a negative 1 squared, which is 1. But c is negative 1, right? So I get minus 1. See what I did there? See what I, sorry. Okay, so 0 is equal to negative a plus 1. So in a puff of algebra, hey, a equals 1. Which tells me this, let's go back to, whoa, let's go back to blue, which tells me that this integral becomes, well, I can rewrite it as a, which is 1 over x plus 1, plus what's b? 2 over, and then b is over x minus 2, whoops, minus 1, sorry guys, x minus 1 squared. And you may be going, Ripley, how are we going to deal with that? Well, that's actually pretty easy, but you've got to be really careful. I'll show you why in a sec. C is, I'm going to leave it as negative 1 over x plus 1. Whoops, that should have been 1 over x minus 1, shouldn't it have? There's too much going on here. My ADD is just a flickering. Minus 1 dx. Okay, now let me give you a word of advice. You notice how I kept this negative 1 here? The reason I did that is really out of principle. Let's say that down here we ended up with some ugly fractions. If, let's say I ended up with a equals 2/7, b equals negative 5/7, and c equals 11/7. Something awful, right? I will always keep my constants firmly in the numerator. So I would rewrite this as, ooh, I'm running out of space. I would write this as something like 2/7 over x minus 1. Plus negative 5/7 over x minus 1 squared. Now you don't have to do this. This is just a preference for me. 11/7 over x plus 1 dx. The reason is it's really easy to take that antiderivative. That would become 2/7 natural log of the absolute value of x minus 1 plus dot, 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 et cetera, et cetera. It's a lot easier to take the integral of it. Okay, now I'm going to turn the page. I'm probably going to have to flip-flop back a couple of times, but bear with me. Maybe not. Let's see what, excuse me, let's see what I can remember. I believe that this becomes, this whole integral becomes, so I'm going to do an equals now. I'm going to get x squared halves plus x, excuse me, and then what I'm going to do is, I think it was plus the integral of 1 over x minus 1 plus 2 over, was it x minus 1 squared, wasn't it? And then plus negative 1 over x plus 1 dx. Is that right? Let's see how good I am. Plus, yay! Okay, I win. Now, okay, let's take this integral and then we'll be done with it. So I end up with x squared over 2 plus x plus, and then this is easy. This is just the natural log, the absolute value of x minus 1. This one's going to be easy too, right? I can go minus the natural log of the absolute value of x plus 1 if I wanted to, and now I can deal with 2 times. Okay, what am I going to do here? Well, if you recall, this is really just the integral of 1 over x squared dx, of course, right? It's got a linear term in there. The antiderivative of 1 over x squared is negative 1 over x, right? You remember that? Because the derivative of 1 over x is negative 1 over x squared. So because this is linear, I can simply rewrite this thing as times negative 1 over x minus 1. Now that's ugly. I'm going to do a little bit of algebra by eraser here, and I'm going to rewrite the whole thing because that was just terrible and it was begging for me to do something screwy. Let's go x minus 1. That's it. Now, a really common error that students absolutely love to do is they'll just flippantly, because we've programmed you to think natural log absolute value, is they'll take the natural log, the absolute value of x minus 1 squared. Mac, no good. Remember, that only works if I've got du over u. This becomes the natural log of the absolute value of u, of course, plus c in both these cases. So let's not forget our c here. If you wanted to get pretty, you could easily pretty this up. I'm not going to waste your time with that. But be really careful, be very deliberate and very mindful of what you're doing when you're doing these partial fraction decompositions, because all it takes is one disrespecting of a negative and all hell breaks loose. Now, I do want to do one more for you. I want to do the inverse, or I want to take the integral of, we're going to do dx over a squared plus x squared. All right, I want to give this one to you. You can memorize it, excuse me, or you can memorize the technique, or you don't have to memorize the technique, but see the technique and use it. Now, I hope you recall that the derivative of the inverse tan of x is equal to 1 over 1 plus x squared. Now, this looks very much like this, but it's not it. The problem is I got this darned a squared in here. So what I'm going to do is, my spidey sense says that I can't do any partial fraction decomposition on this, can I? Because there's nothing to decompose. There's no polynomial that I can factor because it's the sum of two different squares. Unlike back here, we had all kinds of stuff that we could decompose. We factored this, we got crazy with these, but I'm stuck here. So watch this. What I'm going to try and build is, I'm going to try and build du over 1 plus u squared, because I know this is equal, the integral of course, I know this is the inverse tan of u plus c. So I'm just going to build it algebraically. Watch. My biggest problem, as you should recognize, is that I have an a squared. So I'm going to pull out an a squared. I'm going to get 1 over a squared times the integral of dx over 1 plus x squared over a squared, right? I just pulled an a squared out of the denominator. Hey, look at this. Now wait a sec, I'm trying to build that. So if I want u squared to equal x squared over a squared, then doesn't u just equal x over a, right? Because remember, I'm trying to build that guy, and easy peasy. I know that du is equal to dx over a. I don't want a dx over a, I want a dx. Don't think of that thing anymore. That's outside of the integral. This a squared doesn't count, and that can get confusing. This is a du equals dx, which implies, which implies I end up, if I pull that a out in front, I get a over a squared times the integral of du over 1 plus u squared. I have no idea why that stupid circle shows up. So this is equal to 1 over a times the inverse tangent of u plus c. Well, what was u? It was x over a. So this becomes 1/8 the inverse tangent of x eighths. I don't even know if that's a real word. And I'm done. Now notice, no partial fraction decomposition required. In fact, I can't do partial fraction decomposition. Excuse me. However, you can be set up for a failure in this integral because you think it's partial fraction decomposition, and you're like, wait, I can't, what am I doing? That's your problem. Okay? Let's see, I think that's about it. Just remember, a couple of the most important things are, first things first, if the degree of p is not less than, strictly less than the degree of q, I have to long divide. Even if this were equal, I would have to divide it into it to turn it into the setting where I can use partial fraction decomposition. The other thing is, if I have a repetition of a let's see, what did I do? If I have a repetition of a factor, oh, it was here. That's why I don't write this here because it's confusing. I have to repeat that factor. I do a over x minus 1 plus b over x minus 1 squared instead of moving into polynomial zone. All right. I hope that was helpful. Hey, this is the last of our integration techniques, so you're about done. Now we get to use them, and we get to figure out what happens when you can't integrate analytically, which is fun. All right, thanks for your time and attention. Have a glorious day.